So finally, in the last video lecture of this unit, we're going to relate independence, which was the topic of the previous video lecture, to product measures, which is the center of this unit. So before we can make it more meaningful and more general, let's talk about longer products. We spent 4 very long and painful video lectures talking about taking the product of 2 measure spaces that we are now making them probability spaces. Okay, so we have one measure space, we have another measure space. We represent them as lines just because we only have 2 dimensions to write on, and if we want to have 2 spaces to describe, we need to give 1 dimension to each of them. So this is the picture. We have one measure space, another measure space or another sample space. We take the product of them, then we can take the product of sigma algebra of them and product of measures, and talk about switching integrals, etc., etc., etc. But well, as it often happens, what we can do to 2, we can do to any finite number. So we can take finite number of measure spaces. On that, we can take the product, the Cartesian product of those measure spaces, of the sample spaces. So we can take the product omega 1 product with omega n. This is the Cartesian product. Then we can define the sigma algebra, the product sigma algebra, just to be the sigma algebra generated by rectangles, which are not rectangles anymore, they're kind of cuboids of the sigma algebra of each space. And we can define the measure, the product measure, if these are, we can define the product measure as the unique measure such that we assign to rectangles the product of their dimensions. And well, all this, what we did before is just a particular case when we have 2. And as I said, the 2 is the most difficult. The most difficult is going from 1 to 2. Once you can add 2 numbers, we can add 7 numbers. Once we can multiply 2 numbers, we can multiply 7 numbers. And once we can know how to multiply 2 matrices, we can multiply 5 matrices. So the difficult is going from 1 to 2, which is what we already did. Anyway, so we're going to define, let's go back, we're going to define a unique measure that has this property. Well, if there is one, it will be unique by using a pi lambda theorem and uniqueness as before, etc., etc., etc. Basically because this type of set, they form a pi system. Existence, we would need to argue existence, but we don't need to worry about it. Just as we can multiply by induction, here is a 1 possibility. Just take the last one and make the product of it with the first ones, with n minus 1 of them. And well, then you may ask, well, but now is this one defined? Well, this one, it's defined by induction. Yes, this is smaller than what we had before, which means we can take mu n here from the right, and on the left we can take mu n minus 1. We just need to add more parentheses if you want, and we just keep adding parentheses. And we're taking these products always 2 by 2, so it's okay. This will comply with the requirements, so we get existence and we get uniqueness. It's not so important how we got this. It's just clear that it's reasonable that we get this. That if we have a finite number of measure spaces, we can take the Cartesian product of them. We can take the smallest sigma algebra that contains Cartesian products of measurable subsets of them. And on that sigma algebra, we can define a measure that acts as a product measure in the sense that that measure, it factorizes like this. And we're going to use this because we're talking about random variables. And this is the main observation of this video lecture. And now I find it very beautiful how everything connects together. So a random vector, what is a random vector? Is nothing. A random vector is just a collection of random variables put one after the other. Okay? So it's a collection of random variables. What is the distribution of a collection of random variables? It's analogous to what is the distribution of a single random variable. It's a measure, a probability measure on Rn. It's a probability measure that to each Borel set will assign the number or the probability that the random vector is in that set. And here's the connection with the previous slide, with the previous discussion of taking longer products. It is, we have this notion of independence of random variables. And if we combine this definition of a longer product, so this is, I'm taking a product of n measures. So this is a measure, this is a probability on the real line, each one of them. And when we take the product of all these n's, what we get is a probability on Rn. And when are they independent? They are independent when their distribution is actually given by a product measure. And there's it's a very nice formulation. It's a very nice way to think of independence. It's a very mind-twisting new form of thinking about these objects. But mathematically, there's nothing complicated here. So there's really nothing much to justify in this equality. Because what is px1 xn? This is exactly, well, you just look what it is. It is this, which by definition is this. And they're independent if and only if when A is a rectangle, meaning A is of this form A1 Cartesian AN, then we can factorize the probabilities. But this is exactly what it means for a measure to be equal to the product measure of each of these probabilities. So there's nothing really complicated in the equality here, in the sense that to justify it, there is really not much to justify. It's just a different way of thinking about independence, thinking about what it means in terms of measures. It means every computation that we're going to do that involves these vectors, this vector or these random variables together, that those computations can be done on this space, Rn, which is a much more concrete space than this one, and on this space Rn with this sigma algebra, and with the measure, and the measure that we're going to put here will be this will be the product measure, which is a very nice measure to work with. And so the measure P that we're going to put here will be this product measure here. So this is what it means for random variables to be independent in terms of product measures.